Hi, in the previous video, we saw the concurrent futures package, which makes it very simple to farm out computational jobs to worker processes. In this video, we're going to look at another package that helps us handle multi-process programs that don't fit that model. But the pieces are only partly independent of each other. From time to time, they need to pass information between themselves, not just back to the controlling process. We can't do that with concurrent futures because it just doesn't fit into the model concurrent futures uses to describe parallel processing. Or what if we need to be able to cancel a job after a worker process has started running it? Again, that doesn't fit the concurrent futures model. The concurrent futures model is powerful, but its power is based in simplicity. And so, it's not too hard to imagine scenarios it can't handle. When we need to build our own model of how parallel processing should work, we can use the multiprocessing module as the foundation. The multiprocessing module contains a class called process that represents the ability to run code in a separate process. Probably the simplest way to use the process class is to subclass it and override the run method, which is the entry point for code in the other process. In this example, we've created a specific kind of process that calculates some square numbers. Then, we created an instance and started it running. When we called start, the multiprocessing module did the necessary work to make sure that the run method was executed in a new process. By the way, all of the warning we discussed in the concurrent.futures video about pickling and importing modules applies to the multiprocessing module as well. When it comes to moving data between processes and importing code, they work in the same way. So far, we haven't seen anything that we couldn't do better with concurrent futures. But that changes when we start using queues, pipes, and managers. Let's have a quick overview of each, and then we'll look at them in detail. Queues are communication channels that are appropriate for one-to-any, any-to-one, and any-to-any communications between cooperating processes. Depending on how they're used, that makes them ideal for posting tasks to a worker process when we don't care which worker ends up doing the task, and for collecting the results of multiple worker processes. Any process can put a pickable object into a queue, and any process can remove the next available object from the queue. Queues are first-in, first-out data structures, which means that objects are removed from the queue in the same order that they're added. The joinable queue class adds a method which allows a process to wait until the queue has been emptied by other processes. Pipes are one-to-one communication channels. When we call pipe, we get back a pair of objects that each serve as one end of the communication stream. If we give one end each to a pair of processes, they can send messages and data back and forth through the pipe. It's usually best to have queues and pipes as the only connection between processes, because that usually maximizes the ability of the processes to work in parallel. If it's possible to organize a parallel program that way, it should be. If we find that we need to share some variables between several processes, though, we can do it using a manager object. A manager represents a special process with only one job, keeping track of the variables that other processes need. Accessing variables stored in a manager is much slower than accessing a process's local variables, and it could lead to situations where processes trying to access variables at the same time slow each other down. On the other hand, if we actually need shared variables, at least the manager handles them correctly and as efficiently as possible. Okay, let's take a closer look at queue objects. There are three methods that are primarily useful: put, get, and get under bar no wait. When we call put, an object is placed at the back of the queue. When we call get, an object is removed from the queue and returned, unless the queue is empty. If the queue is empty, the process that called get waits until it is able to remove and return an object, which will happen after some other process puts an object into the queue. When we call get no wait, on the other hand, it either removes and returns the object at the front of the queue, or it raises a queue.empty exception. Finally, we could pass a timeout parameter to the get method, in which case it will either remove and return an object within that many seconds, or raise queue.empty. We could pass queue objects around between processes by making them part of the process's initial data, or by sending them through pre-existing queues or pipes, or even by storing them in a manager. Queues are designed to be shared between processes. Moving on, let's look at pipes. Each end of the pipe has the same methods. The interesting methods are send, receive, and pull. The send method accepts object as its parameter and sends it to the other endpoint. The receive method waits for something to be sent from the other endpoint, then returns it. The pull method returns true if there's an object waiting to be received and false if there is not. The pull method can accept a timeout parameter. If we give it a number for the timeout and there's not currently anything waited to be received, the pull function will wait for up to that many seconds for data to arrive, and then return true. If no data arrives before the timeout expires, the pull method will return false. If we pass none as the pull method's timeout parameter, it will wait until data arrives before returning, no matter how long it takes. Like queue objects, pipe endpoints can be sent to other processes as they're launched, or through other queues, pipes, and so on after the process is running. Let's look at Manager in more detail now. Managers can handle many types of data, but we're going to focus on their ability to store dictionaries, lists, and namespaces. Normally, when we send an object to another process, the other process actually gets a copy of that object, which means if the other process changes the object it receives, we don't see those changes in the original process. A manager lets us create objects that behave more like queues, in that if we send the object to another process, and that process changes the object, we do see the changes in the original process, or any other process that has access to the object. The manager dict and list methods create special dictionaries or lists that can be shared between processes. The namespace method, which does indeed start with a capital N, creates a more generic shared object on which we can set attributes to share them between processes. When we have shared data that are being accessed by multiple streams of execution, which is exactly what Manager provides, we have to be careful to keep the data access synchronized. To help with that, managers can also create some standard synchronization primitives, such as locks, events, conditions, and semaphores. Lock objects are the simplest of the synchronization tools. They have a pair of methods called acquire and release. After a process calls acquire, any other process that calls acquire is forced to wait until the first process calls release. Then the acquire call in one of the waiting processes returns, allowing that process to proceed. In other words, code between an acquire call and a release call can count on being the only code accessing whatever data the lock is protecting. Notice that the lock doesn't know what data it's protecting. It's up to us as programmers to define and respect that association in our own minds. Event objects allow a process to proceed immediately if a flag is true, or wait until the flag becomes true. The flag is set to false by calling the event's clear method, or true by calling its set method. When we call the wait method, it will return immediately if the flag is true, or it will pause execution until another process calls set, and then return. Event objects are useful for making a process pause until some specific thing happens. Conditions combine some of the features of lock and event objects. Like a lock, they have acquire and release methods that can be used to protect data from simultaneous access. However, a condition object also has a wait method and a notify method, which can be used to wait until some other process does something and to wake up a waiting process. Condition objects are useful for creating data structures that synchronize access to their contents and wait when they don't have any data to return. The get and put methods of the queue class could be implemented using a condition. Semaphore objects look a lot like lock objects. The difference is that where lock objects always ensure that exactly one process has acquired the lock at a given time, semaphore objects ensure that no more than a fixed number of processes can acquire it at the same time. This is useful for doing things like limiting the number of worker processes that can access the hard disk at the same time. In this video, we saw how to use the multiprocessing package to define what worker processes do and how they interact. In the earlier video of this section, we learned how to use concurrent.futures to make a particularly common multiprocess case extremely simple. So, now we know quite a lot about how to help CPU-bound programs take advantage of multi-core and multiprocessor hardware to run faster. Take advantage of multi-core and multiprocessor hardware to run faster. Most programs aren't CPU-bound though. They're I/O-bound, which means they spend most of their time waiting for input from various sources. Parallel processing doesn't help in that situation, but asynchronous I/O does. That's the topic for our next section.